Coming to this seminar. I'll be giving a presentation that I gave about a month ago also at the Ocean Optics conference. And I think that this work is very nice because it involves so many different disciplines. And I worked a lot together with Susanne Bauer, Costas on aerosol simulations. Anje helped me with looking at orbits, and Matteo helped me also a lot with looking at interpretation of, not interpretation, but the retrieval of actual satellite data. So today's talk is about spaceborne ocean color remote sensing in the UV part of the spectrum. And this work was motivated because of three topics. The upcoming PACE mission, which will be launched in 2022. It's an ocean color mission, but it will also have aspects of aerosol remote sensing and cloud remote sensing. And two other topics that are related to this mission that are the subject of this talk is CDOM and brown carbon. I'll talk about those two things in a minute. So here on the right side you see the measurements that are going to be made by the ocean color instrument on board the PACE mission. It's an hyperspectral imager that will make hyperspectral measurements from the near infrared to the UV part of the spectrum. And it would also make a few measurements in the SWIR bands. The measurements in the SWIR bands are for retrieving aerosol properties that are either going to be used for aerosol studies or for atmospheric correction. And what I mean by that is that when people are looking at the ocean in the visible part of the spectrum where the ocean is not black, of course what you have in between the ocean and the satellite is the atmosphere. It contributes a large part of the signal, up to 90%. So they have to, when people are interested in the ocean color properties, they have first to what they call correct for the atmosphere. They have to remove the atmosphere component to that. And that is why they refer to it as atmospheric correction, but the aerosol community will of course look further into that and actually do research with the aerosol properties retrieved from that. Now what you'll see is that the ocean color instrument will also make measurements in the UV part of the spectrum, and there are several reasons why they want to do that. One is aerosol absorption, and the reason is that when you're looking only at the near infrared, those measurements are not that great to retrieve aerosol absorption. It's not that sensitive, and the reason is that there's not much multiple scattering going on in the near infrared, and so the aerosol absorption impact on the top of the atmosphere is not really enhanced by means of multiple scattering. If you go towards the UV, you have a much more multiple scattering in the atmosphere, and that is because the molecular optical thickness increases several folds, and so that is an ideal part of the spectrum to look at aerosol absorption. But the ocean color community is also interested in absorption by CDOM. CDOM stands for color dissolved organic matter, and it consists of complex organic matter that is dissolved in the ocean, and it gives something like a yellowish to sometimes greenish appearance of waters. Now the reason why people are interested in this constituent of the ocean is that it's very difficult, just like with aerosol absorption, to get information about the amount and variations in CDOM from visible remote sensing data only. And one of the consequences of that is that when they are looking, for instance, at past heritage ocean color instruments that look predominantly in the visible part of the spectrum, it's very difficult to distinguish absorption by CDOM from absorption by phytoplankton. And shown here are two examples of why this is a problem. The top panel here shows anomalies. I should not say anomalies. It shows the difference between two different retrieval algorithms that people have been using to study the ocean color. And the difference is shown here with respect to the retrieved amount of chlorophyll concentration in the ocean. Chlorophyll is a pigment that is contained by phytoplankton, so chlorophyll concentration can be seen as a proxy for the amount of plankton particles in the ocean. And you can see that there are differences between two different retrieval algorithms, and it appears that those differences that are seen here correlate very well with another algorithm that is retrieving CDOM. And so we don't know which one is correct. Is this one the correct one, which explains the differences between the two different algorithms that apparently then do not take CDOM well into account? Or are these differences, or is this picture wrong, and it is that this retrieval algorithm has to be adjusted? To make a long story short, if you're looking at the visible part of the spectrum, it is not easy to distinguish between chlorophyll concentration and CDOM. And that's why they're starting to look in the UV part of the spectrum. And the reason why they're starting to look in the UV part of the spectrum is that shown here is the absorption spectrum for CDOM, this dissolved organic matter in the ocean. And you can see that it increases exponentially towards the UV part of the spectrum. This is the absorption for chlorophyll concentration, which decreases in the UV part of the spectrum. So previously they were using a wavelength around 443 nanometers to retrieve phytoplankton or chlorophyll concentration. But you can see that those two absorption spectra are very similar to one another at this particular wavelength. If you go towards the UV, you start to see much less sensitivity to chlorophyll concentration or phytoplankton, and much more sensitivity to CDOM. So that's one of the reasons why they want to look at the UV part of the spectrum. But one of the absorbing aerosol species, namely brown carbon, exhibits also an exponential increase in absorption towards the UV. And so the question is, how can we distinguish between perturbations in CDOM and in brown carbon if we are looking in the UV part of the spectrum where both constituents have similar absorption spectra? So how can you distinguish between their impact on the top of the atmosphere?
Can you explain what brown carbon is exactly?
So you have several absorbing aerosols in the atmosphere. Of course, you have dust particles that absorb. You have soot particles, black carbon that absorb. Black carbon has a property that its absorption spectrum is constant. It's not constant, but it doesn't vary that much as you go from the visible to the UV part of the spectrum. Brown carbon has a colored amount of absorption. That means that its absorption properties change with wavelength, as opposed to black carbon.
What are the sources?
That is what I'm going to talk a little bit about. It's a pity that Kostas is not here, but perhaps Suzanne can fill in later a little bit more about it. But I'll talk about the big sources.
Can I have one more question? In your previous slide, you showed CDOM, for example, which is predominantly high latitudes and coastal oceans. How is it that PACE, is PACE suitable to resolve coastal waters and high latitudes?
Well, you know, those waters are one of the most complex areas to look at, and it's going to be a challenge. I don't know how well they will do it, but one of the reasons why PACE was designed to have also UV wavelengths is to look at CDOM, which is going to be a lot in the coastal regions. And in the coastal regions, you have also a lot of absorbing aerosols. So PACE at least has the measurements to that have more sensitivity to those two types of constituents than just the visible part. How well they're going to distinguish between those two things is still a matter of research. Yeah? I'll be talking mostly about the open ocean. Yeah? So now, besides the OCI instrument, which is an imager, PACE would also carry two polarimeters that will make multi-angle measurements of the linear polarization of light, SPEX1 and HARP2. Now, SPEX1 will also make measurements in the UV. And so the purpose of this talk is to examine when, if, and how the combination of these two instruments can distinguish between impacts on the top of the atmosphere caused by perturbations in brown carbon in the atmosphere and perturbations in CDOM in the ocean. So I'll first now talk a little bit about modeling. I'll talk about our modeling efforts for CDOM, for brown carbon, where I'll address a little bit your question. And I'll also talk a little bit about what we chose for the scattering and absorption properties of other aerosols and other IOPs. IOP stands for inherent optical properties, and that's a term that is used by the ocean color community. It essentially stands for the scattering and absorption properties of underwater light constituents. That can be phytoplankton, it can be sediments, it can be dissolved organic matter, everything that is in the ocean that absorbs and scatters different from pure water. So I'll talk now a little bit about those modeling efforts. For CDOM, what we did was we used an approach that is actually quite similar to what has been done before about 2 years ago, and it is very simple. What Wei and Al did was they looked at reasonable ranges in the exponential absorption by CDOM in the ocean as you go from the visible part to the UV part of the spectrum. And they used this reasonable range in exponential variations in absorption by CDOM to calculate the corresponding absorption coefficient for CDOM in the ocean. And once they did that, they used those different variations in absorption in the ocean to calculate its impact on the water leaving radiance. And I'll use exactly their same method, except for instead of looking at the water leaving radiances, I'll look at the top of the atmosphere, because that is what PACE is going to measure. So I'm going to use the same method. I'm only going to look at how do perturbations in CDOM, how do they have and what kind of impact they have on top of the atmosphere reflectances in the UV that is going to be measured by the OCI instrument and also by SPEX1. Now the modeling for brown carbon took much more effort. I talked with Kostas a lot and with Suzanne. It's a very complex topic, and there are many different sources for brown carbon, and brown carbon itself can also vary in the atmosphere as it is being transported. It can be photo-bleached, so it diminishes in amount, but it can also be formed in chemical reactions in the atmosphere. So it's not easy to model. And so what I did was I looked at large sources of brown carbon, and one of the large sources of brown carbon is actually biomass burning, smoke that originates from biomass burning. And what they found is that in that smoke they can find brown carbon, which has this colored absorption properties. That is how they define brown carbon, in the form of very tiny, perfectly spherical balls, so-called tar balls. So that's very easy to model. That is what I used. Of course, then I have to know, of course, how much is there in the atmosphere. And analyzers have shown that in smoke originating from biomass burning, what you have is that originally you have a lot of organic carbon that is formed in the atmosphere, and through an aging process, many of the organic carbon particles are then being transformed into tar balls. And measurements in smoke air masses have shown that as the smoke aged, so at aged smoke, the contribution of tar balls to the total amount of particles can be very large, exceeding 70%. And some people have used this large amount of brown carbon originating from organic carbon in their simulations, such as shown here in a simulation by Fang et al. In 2010, where you see that off the coast of Africa, where you have a lot of biomass burning happening and therefore the formation of a lot of organic carbon, they assume that 70% of that organic carbon will eventually be brown carbon. But when I talked here with Kostas and with Suzanne, they doubted whether such high values are realistic, and they suggested that much lower values are also possible, if not more plausible. So what I did in my simulations, I looked at both scenarios. I looked at scenarios where I have an amount of organic carbon and assumed that 70% of that mass of organic carbon is brown carbon. And another scenario, I looked at organic carbon and assumed that only 10% of that mass will be brown carbon. So now that I have more or less gotten my radiative transfer properties ready, that is, I know what kind of particles they are tiny, spherical, I can deduce them, their amount from organic mass. I only need to get a sense of how their absorption properties are varying. And for that I used exactly the same approach as what they used for CDOM. That is, I looked in the literature at reasonable ranges in the exponential increase in absorption by brown carbon and used those ranges to calculate the corresponding single scattering albedo, and from the range in single scattering albedo in UV part of the spectrum, I could then calculate what the impact is on the top of the atmosphere if I have such a range of single scattering albedos in the UV. So that is how I then modeled brown carbon. Yes?
Is it really like this brown carbon or black carbon, or is there also brownish carbon? Is it
what I'll explain a little bit in the next slide what I did. But yes, there are many different aerosol species. You can have brown carbon and black carbon happening at the same time. It's actually very likely if you're looking at biomass burning. But the uncertainty is, if you have here brown carbon being formed and it is then being transported over the ocean, what I'm not taking into account is that during the transport, the amount of brown carbon can vary. It can vary because of photobleaching, it can vary because of chemical reactions. I simply don't have enough information about that. So I'll explain in a moment what aerosol species I'm taking into account. And I'm assuming that with regard to brown carbon, that the amount remains constant as it goes over the ocean. Simply because nobody else has done this kind of computations in the sense of, or in the framework that I'm doing. So I said that I can calculate the amount of brown carbon from organic carbon. So I have to have a sense of the amount of organic carbon in the atmosphere. What I did together with Suzanne is I used simulations by ModelE that was coupled by the OMA aerosol scheme to look at the mass amount of not only organic carbon but also black carbon, nitrate, sulfate, sea salt, dust. So all these particles I'm taking into account, and the simulation results show. So I should take a step further back. What I'll be doing is I'll be focusing on two areas in the ocean off the coast of Africa, of West Africa. And the reason is, as I mentioned before, you have a lot of biomass burning happening in the summer in Angola. That is actually where we just came back from the Oracles campaign that was measuring the properties of these smoke. And OMA is showing that huge plumes of the organic carbon that is originating from that smoke is flowing over the ocean. And so I'm focusing on two areas over the ocean. I'm focusing on box 1 and box 2. Box 1 is much further away from the ocean, so it has much less amount of organic carbon. And box 2 is closer, so it has more organic carbon. Also, the ocean properties of those two boxes change. This is closer to the coastal region, which is addressing your question a little bit. Coastal regions have a very different color of the ocean. They are much more complex to model than when you're going more over the open ocean. So these two boxes really represent a diverse kind of circumstances for both the atmosphere and for the ocean. And the ModelE coupled with the OMA scheme is telling us that organic carbon contributes 36% to the total optical thickness in box 1 and 47% to the total optical thickness of box 2. So that is what I'm using for my simulations, at least for organic carbon. And of course, of this amount, I have two scenarios. 10% will be converted into brown carbon and 70% will be converted into brown carbon. And similarly for this box. The ModelE results show further that sulfates and sea salt are the second largest contributors to the optical thickness in these two boxes. And so for my aerosol simulations, yes, go ahead.
Why is brown carbon not simulated in OMA?
It's really complicated.
But it's, I mean, it's so Jacek's he's using a basic model to translate, but would it, why not just put it in there, even if it's complicated?
We wanted, we quickly had this back before the do so. It's not as easy because, it forms from clouds in the Agnes chemistry, and then it ages, so, it needs special consideration. So, it's not.
It's not as simplistic as what I'm doing here.
It's super doable, but we haven't had the chance.
Are there measurements of this as separate species?
Yeah, there are measurements, but very limited.
So when OMA says it's 36% organic carbon, does some of brown carbon get looped into that category so that it's at least treated somewhat?
So the thing is that, we don't specifically, organic carbon is just all organic carbons together, which is 3,020 species. And some of them are brownish, some are white. Is Andy here? And Andy Laces has put in, like in OMA, organic carbon is a little bit absorbed. So it's, it's not pure white. So it is already considered a little bit brownish. But the thing Jacek talks about is the absorption at this short wavelengths, and that we don't develop. We don't have the chemical specialization.
So what I did was I just looked a lot at the literature, and those two numbers, 70% and 10%, are two very different numbers. And again, as I said before, even when one of those numbers is correct, I'm not taking into account that this percentage of 10% or 70% changes as it flows over the ocean, because as Suzanne said, brown carbon ages. It can be also formed in situ, it can be photobleeds. There are a lot of things that can happen that actually changes this 10% or 70% that I'm assuming. But since nobody has done this kind of work before, I'm happy to present a wrong result if it stimulates a discussion about how to do it better. That's wonderful. But it's important to start with this discussion, as I started it with the ocean color community. And you see later why I presented this at the ocean color community. Yeah. So for the aerosol models that are listed here, I used I assumed spherical shapes, and I used appropriate size distributions and complex refractive indices to model their scattering properties. The exception is black carbon, where I used a sophisticated model for aged soot that I got from Li Liu, that was computed with T-matrix methods, and I believe that she also just published an article about this. So that is how I model the aerosol properties. So I have now the amounts of total optical thickness. I need also now to have a realistic value of the total optical thickness in these two boxes. Rather than using simulations, I used actual data. What I did was I looked at SeaWiFS data. SeaWiFS is also an ocean color instrument. While its purpose is to retrieve properties of the ocean, as I said before, they have to know also something about the atmosphere, because they have to correct for it. And one of the things that they are retrieving in this process of correcting for the atmosphere is the total optical thickness. So for the total optical thickness of those two boxes, I used SeaWiFS constraints, and I looked at the retrieval of the optical thickness over a decade in both these two boxes. Blue is for box 1 and red is for box 2. And essentially it makes also sense, because in box 2 you see a slightly higher optical thickness, which is of course due to the fact that you're closer to the source of smoke. And what I did was I used the average values of these two optical boxes as input for my radiative transfer computations for the atmosphere. And for those optical thicknesses, I of course used then the different percentages that were given by OMA as 46% was organic carbon, and of that 46%, 10% can be 10% can be brown carbon, or 70% can be brown carbon. So it was kind of an elaborate amount of radiative transfer computations that I did for the ocean, for the atmosphere. Sorry, for the ocean, I need also to calculate what the water leaving radiance is, and I used the same approach. I looked at SeaWiFS and looked at what they retrieved over a decade, and shown here are properties of the underwater light. I'll not go into technical terms, but this is for absorption by phytoplankton, this is for scattering by particles in the ocean, this is the amount of chlorophyll concentration in the ocean, which again is a proxy for the amount of plankton, and this is then the amount of absorption by CDOM. And I looked at the average values of these and used that to do my calculations for radiative transfer. Now note that these retrievals are all done for 443 nanometers, so I had to extrapolate that towards the UV part of the spectrum. And I'll just show you one example of how I did that. For instance, for absorption by phytoplankton, what I'm looking is, here is the retrieval for at 443 nanometers, and I use an extensive database for absorption by phytoplankton species that was compiled during the last PACE science team, and they have a huge database of different absorption spectra for phytoplankton. I choose all the phytoplankton spectra that were consistent with this average value, and looked at how the corresponding absorption would be in the UV part of the spectrum. And for absorption by CDOM, I did the same. I looked at, not really the same, I looked at again what the average value is for CDOM at this wavelength, and then I used those models, this exponential increase in absorption by CDOM, to model the corresponding absorption of CDOM in the UV part of the spectrum. So this was modeled, and this is based on real ocean spectrum. By the way, this figure also shows you the problem that they're facing when they're only doing remote sensing in the visible part of the spectrum, which is here. You see in this big arrow here shows the variation in absorption by CDOM, and this red arrow shows the variation in absorption by phytoplankton. You see that they overlap very much. So it's not easy to actually distinguish between absorption by CDOM and absorption by phytoplankton. However, if you go towards the UV part of the spectrum, then you start to see really a big difference. You start to see that those two absorption spectra really become separated. So that is the reason why they're looking in the UV part of the spectrum. So that's an example of how I extrapolated the results from SeaWiFS, from the visible part of the spectrum to the UV part of the spectrum. This, yes.
So is it fair to say that CDOM is actually a class of things that varies around the world depending on where you are,
yes,
rather than being a particular thing?
Yes, it varies around the world. There are several slopes that have been identified for the absorption properties. It's a very complex topic, just like actually brown carbon. There are a lot of similarities between the formation and changes in brown carbon that are also applicable to CDOM. For instance, both species can be reduced by photobleaching, and both species have influences from the atmosphere, and they can also be formed in situ. So it's very complex, and it varies over the world indeed. I don't know how it varies for a particular location. It might very well be that if you stand at a particular location, that the variation in CDOM absorption, the spectral slope, is not that much, but it will differ a lot if you look at another region. So I don't know if the differences are only if you compare different regions, or if the differences are also occurring if you just stick to a certain region in the ocean and look at variations in CDOM absorption properties. I don't know the answer to that yet. Does that answer it a little bit?
Yeah.
Okay. So what I did for box 1 to get the the scattering and absorption properties of the underwater light. I did, of course, also for box 2. And here are the results. And what I did was, again, I used the average values for absorption by phytoplankton, for scattering by particles underwater light, underwater for the amount of chlorophyll concentration and CDOM. I used all of that and extrapolated that towards the UV to do my computations in the UV. So all of this preceding work, the purpose was just one thing: to do realistic simulations for phase-like observations in the UV part of the spectrum, and see how these observations by phase in the UV part of the spectrum vary if you perturb the amount of CDOM in the ocean, and if you perturb, not the amount, if you perturb the absorption properties of CDOM in the ocean, or if you perturb the absorption properties of brown carbon in the atmosphere. And so, so that is what I'm going to do now. I'm going to show you the results for phase-like observations.
Can I ask?
Yes.
Okay, so in this area is very interesting oceanographically because it's a upwelling area. A lot of nutrients coming to the surface. You have large concentrations of phytoplankton. So presumably phytoplankton absorbing at the UV, you would have a big signal just because of the sheer number of phytoplankton. Do you include the phytoplankton in your model simulations? And where do you get it from?
Okay, so I'll go back to this thing here, and there are two answers that I'll give you. What I did was I looked at the retrieved absorption by phytoplankton at 443 nanometers, and I looked at a lot of different phytoplankton absorption spectra to see what the corresponding values would be in the UV part of the spectrum. And the phytoplankton spectra that I was using are part of a large database that was compiled by Zhongping Li. I think they have thousands of phytoplankton spectra. And I picked the ones that are consistent with my observation at 443. Yeah. Now, the second answer that I want to give to you, and that was one of the comments that I got at the Ocean Optics meeting. There was something completely new that I learned that I didn't know about before, and that is they actually said, just as actually you said, that the absorption by phytoplankton can actually also vary a lot in the UV, much more than is indicated here. And it is not related to the amount of phytoplankton, but it is related to a substance that I was never aware of. They are called, I think, microsporin amino acids, MAAs. MAAs are essentially, it's essentially an amino acid that is being used by phytoplankton as a sunscreen. It helps them protect from damaging UV radiation. Now, some phytoplankton species have MAAs and others do not. The ones that have MAAs absorb much more in the UV part of the spectrum because they want to, absorb the damaging amount of radiation. And that would mean that actually there are also phytoplankton species that have a much larger absorption in the UV. That is not taken here into account because the database that I looked at that was compiled by Zhongping Li didn't show that many phytoplankton species that had a large absorption in the UV part of the spectrum. And he explained.
It is a global data set.
It's a global.
This compiles.
Yes. I identified maybe over the 10 years, I identified maybe, shown here are about 43, you don't see that here, but 43 absorption spectra. And there were only 3 or 4 that I'm not showing here, that actually had a much larger absorption in the UV. There were very, very few, a fraction of an amount. And I talked with Zhongping Li about this, and he said, it might be that just that the absorption spectra that he collected to put in his database didn't include many of those types of phytoplankton that have enhanced absorption in the UV. So to make a long story short, it can vary indeed a lot. I don't include it here because there were only very few that I encountered in that database. And I'm just trying to distinguish not be, yeah, I'm just trying to look at the amount that is caused the impact of this variation and compare it with the impact of variation in brown carbon. Yeah, so I assumed essentially that phytoplankton doesn't play a big role there. It can, but I didn't do that. Okay, so PACE observations. Shown here are simulated orbits for the PACE mission for the first half of August in 2023. And you can see that box 1 and box 2, those two areas that are my study areas, are visited up to 5 times in this period of the month. So you'll have in a month a significant amount of observations of those two boxes. On August 12th, 2023, the PACE mission will go right smack over box 2. And so I just plotted here that one orbit, but also included here the swaths by the different instruments on board the PACE mission. The OCI instrument, which is the ocean color instrument, has a very large swath. So it will actually visit box 1 and box 2 much more often. It will observe those two boxes much more often than indicated just by the orbits. On the other hand, SPEX 1, which is indicated here by this white swath, has a much smaller swath. And so that means that SPEX 1 would also only observe box 1 and box 2 up to 5 times per half month in August.
Now that you have cloud.
Pardon me?
Now that you have cloud.
Then it will of course observe less. Yes, then it will of course observe less. Absolutely right. Now when on August 12th PACE is right over the top of box 2, the solar zenith angle will be about 90 degrees, the azimuth angle will be about 0 degrees, and I use those angles for my input for my radiative transfer computations, for my viewing geometries. It varies a little bit, but I'm just assuming that these will be good for a range of observations made as you're going over that box. By the way, these angles will always remain constant also for box 2 and box 1. It doesn't matter where it crosses there, it just crosses there at a certain time of the day, and therefore these angles will be correct for that. Now, in what follows, I will show results for changes in the top of the atmosphere intensity and the degree of linear polarization that will be observed by SPEX 1, the polarimeter, at 385 nanometers. And I'll do that for a range of viewing angles that include the 5 viewing angles that are going to be monitored by SPEX 1. And the results are here. So these are the results for box 1, where I assume that 10% of the organic carbon that is simulated by OMA and constrained by SeaWiFS is brown carbon. And shown here are the perturbations in the top of the atmosphere reflectance if I vary the absorption of brown carbon. That is, if I vary the slope of absorption by brown carbon as it goes into the UV. Sorry, I have to take a step back. This is for perturbations in CDOM. So actually here I'm keeping brown carbon constant, and I'm varying the absorption properties of CDOM, of the underwater light. And I'm varying it, I'm using the different exponential slopes for the absorption by CDOM as I'm going from the visible to the UV part of the spectrum. And the differences are actually quite small here. But one of the thresholds actually for PACE is that the UV wavelengths can be used to distinguish perturbations in CDOM. So in what follows, I will assume that the OCI instrument will be able to distinguish those perturbations. They seem small, but I'm just going from their description and their requirements. And I'll denote the change of the top of the atmosphere reflectance, the minimal change by an arrow here, and compare it later with changes that are caused by perturbations in brown carbon. So again, brown carbon is constant here. Yeah? If instead of changing CDOM, I change brown carbon, you get this amount of perturbation, very small. It's actually even much smaller, or smaller than what I assume is the accuracy for the OCI instrument, if it is indeed that it can distinguish these perturbations. So that means that perturbations in brown carbon cause a change in the top of the atmosphere reflectance, shown here, that is much smaller for this particular case study than perturbations in CDOM. That is good news for the ocean color community. That is perhaps not that much good news for the aerosol community who wants to study brown carbon. Now to simplify my results, I'll use the following color scheme. Blue indicates the range of reflectances, the change in reflectances that is only caused by changes in CDOM. Yellow denotes changes in reflectances that are only caused by changes in brown carbon, and green denotes the overlap between those two sensitivities. So in a nutshell, what I'm trying to do with this simplified figure is that if for a given viewing angle you see more blue, that is good for the retrieval of CDOM, because you have much more sensitivity to CDOM than to brown carbon. The other thing, the opposite is of course true if you see much more yellow. By the way, those 5 vertical lines here denote the different viewing angles that are going to be observed by SPECS 1. So it is going to be observing these radiances here at 5 different viewing angles. Now these are the results for the top of the atmosphere reflectances. If I look at the results for the degree of linear polarization that is going to be measured by the polarimeter, you see actually even a better picture. The amount of green here is even much smaller, which means that you're almost only seeing blue for each viewing angle, which means that each viewing angle will have much more sensitivity to variations in CDOM than to variations in brown carbon. Now these results were obtained by assuming that only 10% of the organic carbon that I got from OMA simulations combined with series optical thicknesses. If I change this 10% to 70%, remember that I had 2 different scenarios. Only 10% of organic carbon is brown carbon, and 70% of organic carbon is brown carbon. So if I change this to 70%, you get the following picture. You are seeing now much less blue for each given viewing angle, and much more green and even some yellow, which means that for this particular case, if it is true indeed that 70% of the organic carbon is brown carbon, it will be much more difficult to distinguish between perturbations in brown carbon and perturbations in CDOM. For the degree of linear polarization, you don't see, well, I should say differently. You see, of course, much more green, but it's not as dominant as for the total intensity, and we also don't see any yellow. So that will provide extra constraints. Another thing that will provide extra constraints is that if you look at the angular variation in perturbations caused by CDOM, that is indicated by this curve here, and this curve here, and this curve here, and this curve here, it shows much less variation than variations in angular reflectances that are caused by perturbations in brown carbon. This is brown carbon, going like this. It has a wavy structure. So one way perhaps of distinguishing between those 2 perturbations is to look at SPECS 1 that is able to provide multi-angle measurements of of the radiance. OCI, which is measuring only intensity, is only looking at one viewing angle. So if you have only the OCI instrument, let's say at this viewing angle, it will be not that easy to see where the different perturbations are coming from. Whereas if you have multiple viewing angles, it provides a bit more information. You have a question?
What is the wavy tell us from the different viewing?
Okay, so
Why is it like that?
why? I thought a little bit about it, and I think there are two reasons. As you go towards the edge of a scan, what you have first of all is that there is less amount of radiation coming out of the ocean. What you have is that the underwater light will be internally reflected by the surface, and this internal reflection is increasing as you go towards the horizon. If you would be totally at the horizon, you would see, not totally, if you are, well yes, if you are totally at the horizon, you would see almost no water leaving radiance at all. It just doesn't escape out of the ocean. So as you go towards the larger viewing angles, you have that less light is coming out of the ocean. At the same time as you're going towards the larger viewing angles, you have that the air mass becomes larger. The path that a light is going through the atmosphere is becoming larger for larger viewing angles. If you're going only straight up, it only goes through the thickness of the atmosphere. If you're going at the slanted angle, it is going through a much larger amount of air mass. And that means that brown carbon perturbations have then a bigger impact because light is encountering brown carbon many more times. So at the larger viewing angles, you have less water leaving radiance and you have more impact of brown carbon. That doesn't really explain why you have here this bump here. I have to do a little bit more research on that. My suspicion is that, remember that remember that the sun azimuth angle is 0 degrees. So actually it is observing a sun glint. And you see that bump exactly happening you see this bump exactly happening where the sun glint is. And I suspect that it has to do with the sun glint. I have to think a little bit more about why the sun glint is impacting the impact of perturbations in brown carbon. So there are two possible reasons: outer edges and sun glint. Yes?
So this is for one wavelength.
Yes.
Both OCI and specs have quite good spectral resolution. So what is the difference in spectral?
That's a very good question. I didn't have time to look at this. To actually compile the amount of input for just these simulations took me about 1 to 1.5 months. I had to do a lot of research on the different aerosol species, on get acquainted with OMA, get acquainted with SeaWiFS. So it took me a lot of effort, and I concentrated only on one wavelength, but you have a very good question, and that is what happens with this variation that you're seeing if you're going to look at other wavelengths. I chose 385 nanometers because that was the shortest wavelength that is going to be observed by the polarimeter, by SPEX1. So 385 nanometers is still going to be observed by both OCI and SPEX1. To get a better picture, I should also include wavelengths that are larger, 390, 95, 400, and then look at that picture. If I go at smaller wavelengths, I don't have SPEX1 anymore. The other thing that I'll mention with regard to your question is, I looked here only at the degree of linear polarization. And that is because I have a sense of what the accuracy will be. I showed here with the arrow that it will be 1.5 to 2%. I could also look at just the polarized reflectances, and I suspect that there you'd have a bigger sensitivity that you can use towards distinguishing between perturbations in the ocean and perturbations in the atmosphere. The problem is that I don't know what the accuracy of those measurements will be. What I mean by that is it will be I should take a step further back. What the ocean color community is doing is that when they are looking at measurements at the top of the atmosphere, we know from instrument calibrations that normally measurements are about 3 to 5%, the uncertainty. For the ocean color community, that is too big. So what the ocean color community is doing is they are doing also vicarious calibration. Once the instrument is up, they are making measurements at the surface and comparing those measurements with the measurements that are done by the satellite. And from that, they are going to get a sense of how can we improve the calibration of the satellite in order for those two things to match with one another, satellite observations and surface. That is what they have been doing for the total reflectances. I presume that they would also want to do that for the polarized reflectances. I don't know of any plans, but I don't know how accurate that would be. So I do know what they can do for the total reflectances. That's why I'm saying that I presume that they can distinguish this, but they have not done that yet for the polarized reflectances. So if I would see differences in the polarized reflectances, I have no metric yet to say yes, they can distinguish it or not. After vicarious calibration.
If you calibrate the total reflectance, then you calibrate the
That's actually a good point. I didn't think about that. That's a very good point. What I can do is I can take it's a very good point. I can take the product of the total and the degree of linear polarization, which gives me the polarized reflectance.
Alright, you uncalibrated the FDLP.
Yes. That's a good point. I didn't think about that. That's a very good point. It's on my list to do. It's on my list to do.
Jacek, if you set the optical depth of the aerosol layer very high, very high, would
Yes.
that line get flattened?
Well,
I mean, there's no directional property in the reflectance that you would expect. Angles.
these are just perturbations. So it's not the measurement itself. It's the change in the reflectance. Yeah, that is showing some angular dependence. But you're right. If you're
If you
looking
just
at
put
the
it
total,
very high, you would essentially measure the BREF of that brown color.
yes, yes. If you know, but it's logical. If you put more stuff in the atmosphere, your top of the atmosphere observations will be much more sensitive to what is out there in the atmosphere.
Right.
And
You
much
would,
less to-
eliminate possible directional properties of what's below. It's just isolated to effect.
Yeah, but you know the bidirectionality of water leaving radiance is actually quite small.
Right.
It's if you see any bidirectionality, it will be mostly coming from the atmosphere, and you can have different aerosols. For instance, what they're doing for Miser is they say that they can retrieve the non-spherical dust particles by looking at the bidirectionality. That is what they say, but I'm not saying that that can be done or not, or not commenting on that. All I'm saying is that if you're seeing bidirectionality, it will be mostly coming from the atmosphere, not from the ocean. Okay, so this was for box 1. So if you go to box 2, the situation changes a little bit. What are the changes? If you go to box 2, you're closer to the coast, and that means that the ocean is actually going to contain more dissolved matter that is coming from the coast. That will make the waters darker. You're also closer to the source of the aerosol, which means that you're going to have a larger optical thickness of the atmosphere. And those two things will actually reduce the sensitivity to the ocean color, because the ocean is becoming darker, and increase the sensitivity to atmospheric properties because the optical thicknesses they are larger. So if you're now going to look at box 2, this is first box 1. Remember, this was the picture for box 1, and I'm now going to look at box 2 for 10%. that is here. And what you're seeing here is indeed green becomes larger and blue becomes a little bit smaller, which essentially is saying that you're going to get less sensitivity to CDOM, the reason being that the ocean is darker, so it contributes less to the top of the atmosphere. And you're going to be seeing more sensitivity to changes in brown carbon, because you have simply more brown carbon there. But still, for this particular case, you still see a lot of blue for each viewing angle, which essentially means that you can still do here a nice job in retrieving CDOM if you have only 10% of the organic carbon that is brown carbon. You see also less optimal situations for the degree of linear polarization as compared to box 1 for 10%. But still, you see that there is much more blue than green, which means more sensitivity to CDOM than to sensitivity in brown carbon. Now, if we change this to 70%, this is what you're getting. You're seeing no blue at all in either picture. And that means that you have nowhere a sensitivity to only CDOM. You'll see only sensitivities that are caused either by CDOM and brown carbon or only by brown carbon. So this is going to be a very difficult case to distinguish between brown carbon perturbations and CDOM perturbations. And what I think is going to be important then is to look at the bidirectionality of the top of the atmosphere results, where you do see a difference between perturbations caused by the ocean versus perturbations caused by the atmosphere. And similar conclusions can be drawn here for the degree of linear polarization. So there are just 4 simple things that I want you to take away from this. That CDOM and brown carbon have similar absorption spectra. They both increase towards the UV part of the spectrum, and variations in their spectra are extremely similar. I was very surprised to see that even the changes in slopes for absorption by brown carbon are very similar to changes in the slopes for absorption by CDOM. It's very, very similar. The amount of brown carbon can be significant if you are looking at areas that are affected by biomass burning, such as off the coast of West Africa. How big that amount is uncertain, because the percentage of organic carbon that is actually brown carbon is uncertain. It can be very high, as some people argue, or it can be very low, as is more favored by, I think, Suzanne and Costas. But we don't know what that number is. Unfortunately, as Suzanne was in Oracles a month ago, looking exactly at this biomass burning smoke coming off the coast of West Africa, there are also measurements being done that can show us a little bit more about what kind of percentage of organic carbon is brown carbon. And so I'm eager to wait for those results, so that rather than using 10 or 70%, I have perhaps a more realistic number. The impact of brown carbon on the UV radiance can be larger than that of CDOM, again for the extreme case. If the numbers are changing, then perhaps the impact is not as large. And multi-angular UV measurements, at least in this particular study, which is only focused on one wavelength, can be very useful in distinguishing between those 2 impacts if they are similar in magnitude at the top of the atmosphere reflectance. So thank you.